So today we're happy to welcome again Professor Aluffi for his second lecture on Segre class and other invariant in intersection theory.
Thank you, Mboyo, and thank you all for being here. So, I think my first task is to finish yesterday's talk or something. Of course, I did not go as far as I was hoping, and now I have to kind of shuffle things around a little bit. Maybe the first, let me start with something that is really very much similar to what we did yesterday. Yesterday, if you paid attention, the key computation was to evaluate the difference between intersections of proper transforms and intersections before you take a proper transform. So what was, maybe I should attempt to set the stage again. I was taking something living in a variety, say a subscheme, and blowing it up. This map is pi. The graph is here. And I computed the following. I computed the difference between a number you can compute maybe, or a class. I told you, this may work very well in, for example, the Chow group. The intersection product of a number of things in here. I use hypersurfaces. I will keep using hypersurfaces today for a little while. And the product of the proper transforms upstairs. And given the context that this came up from, these were the especially this. It was, and maybe I should be precise at least once. This was the pullback of xi minus one copy, exactly one copy of the exceptional divisor. This was part of the setup. I'm not going to retell the story for obvious reasons. And what we found was that this was, in fact, computed by, let me write it the first way I wrote it, by something that comes from downstairs. In fact, it is downstairs, and something that was defined for this purpose. And then you have to look at the piece of in the correct dimension. So if these are hypersurfaces, it would just be the dimension of V minus n. And this was part of the motivation, or the motivation, to define this object as I did. That is pi lower star of this alternating sum of powers of the exceptional divisor. Okay, this is one thing we did yesterday. One thing I want to do, just essentially to warm up, is upgrade this a little bit. Now, the problem I used as a toy problem yesterday was the intersection that you have to look at if you want to find the number of conics tangent to 5 lines in general position. That's a nice example because it's very easy to understand. Otherwise, there's a more famous example, right? The number of conics tangent to 5 conics in general position. So what would the story be in that case? I'll use this as a motivation for a computation I want to do. Here, as far as I know, there's no duality trick that immediately tells you what the number is. So really, what you have to do is essentially what we did over here. But there are complications. In this case, you're looking at hypersurfaces like this. If you fix a conic, see, number of smooth conics, yeah, something is missing here, right? Why don't you complain? People should complain. Tangent to 5 smooth conics in general position. So let me fix a conic. Let me not do the computation that leads you to realize that the hypersurface of conics tangent to C happens to be a degree 6 hypersurface in P5. Remember, yesterday we were intersecting quadrics in P5. Now we have to upgrade this to a degree 6 hypersurfaces. And it is exactly the same problem as we did before, because there are conics, these conics, which, silly, I mean, they think they are tangent to anything, right? Because the intersection of that conic with a nice conic C is a double point, or maybe two double points that this happen, but it is something that counts as tangent. So the problem is the same. Now, if I have nice conics, 5 conics in general position as much as you want, this will be the number you want. And then union a locus, and the locus is the same. It's the Veronese surface. So if you are overly optimistic, you say, aha, we solved the problem already. Here's the solution. I just need to do this computation with 6 instead of 2, and I should get the right number. And that is not right. Why is it not right?
Because math is inconsistent.
No. Fortunately, not because math is inconsistent. It is not right because in the other case, I, of course, swept this under the rug, but we were really lucky. If a local computation will tell you that the intersection of quadrics you were looking at would be y scheme theoretically, while the intersection of these guys along y is not y scheme theoretically. It's some thickening of y, if you want to think of it that way. But the geometry is almost as nice because you can check if you are patient that, well, number one, each of these xc has multiplicity 2 along y. So you see, that affects this computation. Here I was assuming that this would be pi upper star of xi minus e. Here I will have that the property transform, if I want to use the symbol up of c, is a pi upper star of xc minus 2e. Right? That's the difference. That's the bad news, or some difference between with respect to yesterday. But the good news is that the situation is almost the same geometrically. After the blow up, along the same y. So this is, I'm not thickening y at all. I'm just blowing up along the Veronese surface exactly as I did yesterday. It just so happens that the intersection of 5 of these in general position and the exceptional divisor is empty. So somehow the blow up has the same effect of separating the hypersurfaces along the Veronese. Only I cannot use this, because this was assuming that actually y was cut out scheme theoretically, and this is not the case here. So I want to deal with that. Is the difference reasonably clear? Something scheme theoretic that happened yesterday will not happen here. But you still have control on the situation. There's beautiful geometry, and I think this is worked out very carefully in a paper by Fulton and McPherson that in which this was used as an illustration of their techniques. So they can tell you exactly in what sense, what it means for C1 through C5 to be in general position so that this would happen, for example. Now, this can be figured out. But I want to access this situation from maybe a slightly more general perspective and do the following. Assume that, so more generally, let me get away from the example. More general situation, assume that you have a number of hypersurfaces, x1 dot xn are hypersurfaces in V, and assume that y is inside V, and assume that xi is, no, I have the same blow-up picture over there. Not that I need it, but just so it's here to comfort me. There we go. I'm assuming that xi tilde, the proper transform of xi, is the pullback minus mi. So I'm allowing xi to have multiplicity mi along this. And now I'm not wondering about whether y is a scheme theoretical intersection or not. I just want to evaluate the difference between what I've written over there, between the intersection product of the xi's and the push forward of the intersection product of the proper transforms. Maybe I'm very lucky and something like this happens, so that will actually compute the number I want. Maybe not. All I'm aiming at is computing this difference. If I blow up along y, how does that affect the intersection product? I'm making such a long introduction for what is a very, very mild variation on the computation we did yesterday, but I want to carry it out. In fact, I will just do it. Here it is. It will take 2 lines because we did the same yesterday, essentially. So I will just need to remind you of a very simple computation. So this time I have to do the same, right? I take this same point of view. All I need to do is formally this computation. I think I had a semi-clever way of writing this. That's too kind. What would you do? No, this is going to look really silly, I'm sorry, but no, this is now a formal game, and these are variables. I just need to understand how to manipulate this. I just divide by the multiplicities. What if there's 0? I don't care. No, I'm taking everything here as a variable. Let's just do that as function, as a polynomial. This is the same as 1 over m1 and n, and then x1 over m1, which means nothing really. But, yeah, this is a formal game at this point. What a student of mine who will remain nameless and who is not in this room accused me of just doing high school algebra. It is high school algebra. And what do I need to do here? I need to do x1 over m1 minus e dot xn over mn minus e. Close parentheses. Aha, this is exactly what we did yesterday, except that yesterday I did not have this thing, and yesterday these things were called x1, xn, instead of being called x1 over m1, xn over mn. But you see, I'm exactly in the same situation. I'm taking away one copy.
Multiply by
Yes, you see, I cannot even do the high school algebra. m1 dot mn. I want to divide by m1, which means I want to extract a factor of. Thank you, Bernard. This is key to the actual solution of this problem. So you see, we did this yesterday. I can use the same computation. That would be m1 dot mn, and then I can take the piece of dimension whatever, dimension b minus n in. What do I need to write over here? I need to write 1 plus the thing that took the place of x1, 1 plus the thing that took the place of xn, and here I will have the Segre class of y in V. Y does not care that it is not cut out scheme theoretically by the xi's. This is a formal computation that simply works. Okay, and then I can, of course, bring the mi's in again. Maybe I should write it over there, because that's the final answer. This is something that looks a lot like what we did yesterday, but it's not quite the same. Now, if you multiply by m1 this term, what you get is the multiplicity m1 plus x1. Dot mn plus xn, Segre class of y in V. Piece of dimension. Okay. Took me like 15 minutes to just upgrade the formula from yesterday by replacing the 1 with the multiplicity of x1 along y. But this is a very handy formula. I've used it many times in computation. You see, if you wanted to use what we did yesterday, you really had to kind of go through a headache and figuring out how to blow up V along a potentially complicated scheme theoretic intersection of things. Now I don't need to do that, because if we go back to the example, the y is the same. It's the Veronese surface. I've already done the blow up. I've already computed this. If I want to solve this problem, assuming that I know this, I just need to apply this guy. And have I made a point of some sort?
Multiplicity of pairs of ideals.
Looks like something good.
You're fixing an ideal y, and you don't worry anything else about it, and you're pulling that up, and then you're looking at how the other things.
Yes, somehow it's shifting a burden. I could have introduces those multiplicities as coefficients in the powers that the exception relies on. That would change this guy. I did not want to do that. I wanted to kind of transfer the information back to here. And computationally, that is a little nicer because then I already had this. If I've done my job yesterday, it's usually easier to do a blow-up if this is easier. So this allows me to deal with situations in which the scheme may be more complicated than I wanted. I'm erasing this. Is that wise? No. But let me go back to the example. Because by now you know I like numbers, and so we are talking about 5 conics in general position. That's a famous problem. Let me just show you what happens if you apply this trick to this situation. If I may, this is the wrong page. This is the right page. So this is conics tangent to 5 conics. You know what I'm going to do, right? I'm going to compute this power series. So the number would be x1 dot x5 minus that thing over there. This is coming from the zoo, and I told you each of the hypersurfaces is degree 5, so this is a number. It's the wrong number, of course, right? We had to correct it by a correction, which that allows me to compute. I'm not going to recall the notation from yesterday because they're on video, right? So the poor people who may be watching this after the fact can just rewind. But I had H as the hyperplane in P5, big H was the hyperplane in P5, little h was the hyperplane in P2. And in this case, I told you my multiplicity is 2, that's my Mi. And here I have 2 times 6, all right, or 6 times 2, that's somewhat different. Now this is the pullback of the hyperplane to the hyperplane in P2 and degree 6. There's 5 of them. And the same class we computed yesterday, I computed this for you, so you have it. 1 minus 9h plus 51h squared. And then terminal dimension 0, so deal with this as a number. Let me just show you how it works out, because I like numbers. I like big numbers. This is 2 to the 5th I may remember. The other terms I don't remember. These are maybe not worth going to such length for this, but this is what it turns out to be. 4, 5, 1, 2, h squared in dimension 0. Dimension 0 means coefficient of a square, so 7, 7, 7, 6 minus 4, 5, 1, 2 equals?
3264.
Of course, 3264. This is a famous number.
Is that what Tony said yesterday? Quickly?
Yes.
No, you're thinking of.
Had the problem. That was what he was thinking about, yes.
Very good, Tony. You're looking at data.
Okay, so this is an example. I've used this formula quite a bit. This is a handy formula. Now, you are not assuming that the hypersurface is just separated after the blow-up over time. You just control how an intersection number changes after a blow-up. If that is your task, then I can suggest that you use this. It's quite handy. Okay. So that was task number 1 I wanted to accomplish. Sip of decaffeinated coffee. I'm not sure that that helps, but let's see. What else? Questions about this business? Okay, so the first 15 minutes were advertising this guy. I'm not going to use it again, but in case you're doing computations with blobs, this may help. So back to Segre classes. There are 2 here, but I wanted to say more about Segre classes. What do we know at this point? We know that Segre class is defined in some fun way. With the usual notation I used, it's this guy. One thing I convinced you of the other day is that if y inside V is a regular embedding, so that it has a nice normal bundle, then S of yv is the inverse Chern class of that bundle. This is how I computed this, for example. if you remember what we did yesterday. So for example, by the way, I should point this out, if y is D, a divisor in V, just a hypersurface, its normal bundle is 1 plus D, and let me use this shorthand for this guy. It's I'm applying to D the inverse Chern class of the normal bundle. So if you like expansion, this is what it is. Okay, that's the point to be made. There are other problems and properties of Segre classes, and I considered giving more of a sketch of a proof, but let me just draw a diagram. So these are more properties. If you stare at this diagram, you can do this yourself. Probably it's not useful that I do this for you. I'll draw the diagram and then say what these things are. You have to draw it so that it's nice and three-dimensional. There you go. You see what I'm doing, I think, right? There you go. This is the proof of what I'm going to write over here. I'm assuming that I have a map, a morphism from V prime to V, and I'm calling y prime the inverse image of y. Of course, scheme theoretic, right? This is done all scheme theoretically. This is a sub-scheme of V prime. One arrow is missing, and you're not telling me. And then this, the front face is what you would use to compute the Segre class of y in V. The back face is what you would use to compute the Segre class of y prime in V prime. And then, depending on the quality of f, you can use the diagram and chase it to figure out that if f is proper, then the push forward of the Segre class of y prime in V prime equals the degree of f times S of yv. Proper allows you to push forward, so this makes sense at least, and it is true. And if f is flat, then the pullback of, or I need to just write S of y prime v prime equals the pullback of syv. Saying this quickly because they will not play a big role, but maybe the first one is something to focus on. So the moral is that if the maps are nice, then the Segre class behave in a very controlled way. So for example, and this is probably the most important example, assume that f is proper and birational. Then this tells you that the push forward of the Segre class of the inverse image equals the Segre class. Degree f equals 1. So then you have f lower star of s y prime v prime equals s of y. Okay? So in fact, one reason why I'm putting this on the board is that it's a good mnemonic for the definition of Segre class. Suppose you have a class that satisfies this. The Segre class, you should complain because I don't write things where I should. This is SDV, that was missing. This Segre class equals that. So as a little aside, assume that a class satisfies number one, if D is divisor, then you get D over 1 plus D. And number two, this property. This is a birational invariance, I guess, of Segre classes, right? They are preserved by birational maps. Number one, for a divisor, you get what you get for a Segre class. And number two, it's birational invariant. then that class is the Segre class. Which is remarkable. You need to know very little about the class to conclude it is a Segre class. I mean, if you have a way to associate a class to a situation like this that satisfies these two properties, then it is a Segre class. Do you see why? Do you see why? I mean, yes.
Because you can do blow up,
Thank you.
turn things into divisors.
Precisely. Blow-ups will turn any embedding into the embedding of a divisor. Given y inside V, the blow-up of y of V along y to V is a proper birational map. So by birational invariance, you get the Segre class of y in V must equal pi over star of the Segre class of the exceptional divisor in the blow-up. And the other property tells you that for an exceptional divisor, that's what you get. Which is why when I give shorter talks and I have to really quickly say what the Segre class is, I say, well, it's a class that satisfies this and that. That's enough to do to Okay? That's something that's pleasant to keep in mind. What else is on my agenda? One item I have is multiplicities. So I'm listing things about Segre classes, right? This is one property, this is another property, third property. This is a consequence, that's a consequence of the consequence. Let me just erase this, I don't think I need anything more. Let me show you the example. I think in terms of examples anyway. Let's take a plane and a curve. I don't think I need to do anything. Do I want to draw a fancy picture? I had a fancy picture, no fancy picture. I don't care. This is C, and this is a point P. What's the Segre class of P in C? It's a class on P, so it is some number. It's a point where the curve may or may not be singular, yes. P is this point in this picture. And the question is, what is M? And this is a little exercise at this point, because I can blow up along P. You see, initially I was blowing up along the thing I wanted to the Segre class of, that's exactly what I'm doing here over here. But no, in principle, you should not blow up the plane. You should blow up the curve. But no, blow-ups are very nice. They satisfy nice universal properties. So the blow-up of the curve at the point is the same as the proper transform of the curve in the blow-up of the plane at the point. Proper transform. So my definition is that the Segre class of P in C should be a push forward of the exceptional divisor of the blow-up of the curve C tilde, that is E dot C tilde. So it's a contribution coming from this point. These points you're seeing are the exceptional divisor of the blow-up of C. No, they may have multiplicities, who knows? And then this tells me what the story is, because this is well known to be the multiplicity of C at P. Okay, so the slogan is that Segre class is no multiplicities. The coefficient of P in the Segre class of P in C is the multiplicity of C at P. And this generalizes somewhat easily, more generally. The word easily is dangerous because usually you say something very stupid as soon as you say that something is easy, right? Let's see. I think what I want to have is y, an irreducible subvariety of v, say a variety. Then what you get is that SYV is a class on y. It has a multiple of y to begin with, plus lower dimensional terms. This number over here is the definition, is by definition, if you want, the multiplicity of v along y. And it agrees with other notions of multiplicity. The Hilbert-Samuel multiplicity would be the same number, actually. Okay, here I'm just advertising things. Here's one more advertisement. You can compute multiplicities if you can compute Segre classes. This is a strategy that works well sometimes. You want a multiplicity here. You compute the Segre class by blowing up, push forward. That will compute the Segre class and tell you what the multiplicity is.
Does Singular compute Segre classes?
I don't know about Singular, but Macaulay 2 does. I have.
There's a program called Sugar.
That's a program called Schubert 2 now that computes Segre classes of vector bundles. But for Segre classes of subschemes, there are packages. I wrote something back in 2003, but other people have done better job. Maybe I should list the number of them. If you look for Helmer, that's probably the state of the art. But yes, Macaulay 2 now has a package you can load that will compute Segre classes. How will it compute it? That's a very good story. But
You realize this also is a self-intersection number of the exceptional divisor of the law from the curve at P, right?
Self-intersection, yeah, I suppose. I mean, the way I think of this is that I'm doing E times the pullback of C minus, sorry, n times E, where this is the multiplicity. This m is the same as this m. Okay, so these are just remarks. I'm afraid that most of this lecture will be a sequence of remarks like this. Let me put on the board a sad computation. Or maybe before the sad computation, let me write something that will show why it is sad. Now, you look at Segre classes, you find that they have all this information. You want to compute them, and you start looking for ways to compute them, for example, because maybe then you can implement them. So let me do a little observation in the case in which I have y inside x inside v, and x is regular embedded in v, while y is regularly embedded. I simply cannot spell this, right? In x. Why do I do this? So I can compute the Segre classes. This Segre class of y in x will be the inverse Chern class of the normal bundle, cap y. This is a class of y in v, Chern class of n y v, inverse cap y again. So what kind of computation can you put together? Well, there's a sequence, right? There's a sequence. 0 goes into normal bundle of y in x inside the normal bundle of y in v. I'm assuming, oops, this is supposed to be a v, right? No, x is fine. I think this is what I need. I hope I didn't mess up. I should put a pullback over here, of course. Let me just ignore pullbacks as always. I just cannot keep track of them. So unless I've written this wrong, and if I've written it wrong, you will tell me, and I will correct it if I manage. The Segre class of y in v by this sequence is the inverse of y in x, inverse of x in v, cap y. Have I lost? I mean, these kind of computations are really boring to watch as someone does them, right? This is a problem in calculus or in any other talk whatsoever. But here you probably went into autopilot as I did, there's an obvious sequence to look at, will give me an obvious relation of some sort. So what I'm writing is truly obvious. This nxv inverse cap y might have appeared already. It hasn't. So maybe I should get a little worried here. Have I written this wrong? No, I've written it right, but I wanted to write it in a different order. So cap this with that. And what you get is the Segre class of y in x. What you're left with is the Chern class of x in V. What I'm writing is distressingly obvious. That's the whole problem. So I can write this nice formula. In this situation, the Segre class of y in x is the Chern class of n xv, Segre class of yv. You run into this and you're very happy, because then whenever you're running into such a situation, you will know that you can compute this class by knowing the other ingredients.
The inverse, right?
I think I moved this.
You did it right. You put it on the other side. This high school algebra is good this time.
Okay.
Thank you. They will not take away my license, I suppose. Not for this in any case. Okay, so this is obvious observation. It's also useful, but let me put maybe next to this business a side computation, calculatrist. What if I do this with y equals a point as an element of C, which is my x, a curve inside P2. So I'm kind of looking at this over here, right? This was P2. That's why I left this picture. I wanted to have something like this on the board. Then what is S of yv? Well, that's a point in P2, and I just told you that the Segre class computes multiplicity, so this is just the point. Right? And if that is the case, then I'm telling myself to organize this computation this way. This is just a point. If you hit a point with a Chern class, you don't change it. What about SYX? This is y, this is x, right? This is y, this is x. For this guy, say this is nodal cubic if you want. No? That would be the multiplicity of the curve at the point, maybe 2 times b. Just make up an example in which the multiplicity is not 1. Isn't that a problem? Because here I have SYX, which is 2 times p, and that did not turn out to be the same as C of nxv SYV. I like drama, right? Here I convinced you that it was completely obvious that this formula should be true, and here I convinced you it's completely obvious it is not true.
I told you mathematics is in
Yes, David has a point. What is the problem? Let's see if you paid attention.
regular embedded.
Exactly, right? The problem is that the point is not regularly embedded in the curve. So this does not work. I'm jumping up and down for the audience because it's really tempting, seductive to do this in a case and they say, oh, come on, it must be true in general, I'm going to use it. Don't do that because this thing is completely obvious when it works and it is simply not true when it doesn't work. And,
No,
so,
not true.
That's a little sad, but it is simply a fact of life. So avoid trying to use this unless you know that it is really true. So this looks right, but not true unless the hypotheses are met, which is not surprising, I guess. In particular, this guy.
And you didn't say that x and y were smooth, right? They don't have to be.
If they were smooth, then this would work because they would be regularly embedded automatically.
But in particular, it works for singular.
Yeah, this will work even if they are singular, so long as you have a normal bundle, basically. Yeah, local complete intersection will be fine. Yeah. But be careful, unless you have that. So that's the bad news. Now this has played its purpose. Maybe I can sneak in this part of the board. A happier computation, that is, which I'm not going to justify, I'm afraid, because it would take too much time. But now, along with Boyo, I'm going to assume that V and W are non-singular. But Boyo wanted more. If Y is also non-singular, then I'm in that situation. I'm relaxing that, if you want. This doesn't mean that Y should be regular embedding V. I just know that this part is good. And then I have an arbitrary Y any. And then it just so happens, this is a theorem, and I see that David has brought in his copy of Fulton's book.
He's got his too.
Right. So if you look up section 4.2.6, example 4.2.6, then you will discover that this class is, in fact, that formula, the box, is OK in this case. So that's remarkable because the hypotheses are not quite right? I'm not requiring all those embeddings to be regular, but so I guess this makes this statement a little too harsh.
I've been there for hours.
So this is true.
I was already reading to the next page.
This is the Fulton police, whatever you said.
The Fulton police is, yeah.
This is the original.
Hi, Bill.
I have two of those.
They are essentially identical.
These are the Fulton Manics.
OK. No. So why is this nice and why am I doing this? Right now, number one, to advertise an interesting fact. Number two, because I think I will need what I'm writing over here in hour number 2. How am I doing? Not so well, actually. So as a consequence, if Y can be embedded, actually, let me just rewrite this otherwise. In this case, I have tangent bundles all over the place. This is tangent bundle of W or tangent bundle of V. So what this is saying is that C of TV cap SYV equals C of TW cap S of W, YW. Maybe my calculatrist can give me it now. What's written over here? What's written over here is that if Y can be embedded in something non-singular, then this will not depend on the place where you put it. Put it in V or put it in W. If you do this computation, you get the same class. It does not depend on V, so I can just call it, well, I don't need to take along the notation V. It's a class, it's a canonically defined class for any embeddable subscheme. I call it CF because I called the Chern Fulton class. And again, no, Fulton. 4.276. If you want to see the proof of the fact, it's not something I can summarize quickly, and you have to look in Fulton's book. OK, so this, that in my mind, that's the theme of the third hour. That is, next hour is Chern classes you can associate with a scheme. This is one of them. This is a canonically defined class you can associate with a scheme. If Y happens to be non-singular, then what we are doing is TV divided by normal bundle cap V, so we get the tangent bundle back. No. Let's say that too quickly. If Y is non-singular, then CFY equals C of TY cap Y. It's a generalization of the Chern class of the tangent bundle that you can write for any embeddable scheme. And as we will see next hour, it's not the only choice. There are other possibilities. OK, that was something I wanted to get through. and I'm not doing so well in time. We started like 3 minutes late, so I still have.
Pretend we started 5 minutes.
Okay, I still have about 15 minutes, I suppose.
I'm going to say something about the degree of that class.
The degree of the class. So the by degree you mean what I mean when I write this, right? I don't have a nice general statement, but if y is a hypersurface, I don't want to say something just wrong. In fact, let me not write something wrong. I can say it and then maybe it will be forgotten. But for example, if y is a hypersurface you can smooth out, then this is the Euler characteristic of a smoothing. Put yourself in projective space, take a hypersurface of degree d. You can compute the Euler characteristic of a smooth hypersurface of degree d. The degree of this, in fact, the whole class will agree with that. Maybe I should write it. It's a nice observation. Thanks for bringing this up. Because it's a computation we can do, right? Let me put myself in. I like concrete examples. So say that X is a hypersurface of degree d in Pn. What is Cfx? Well, the definition is this is C of Tpn cap S of X Pn. C of Tpn, we know it's 1 plus h to the n plus 1. That comes from Euler's formula. I already used this fact a couple of times. And the other piece we also know, because it's a hypersurface, so it's regularly embedded as a divisor. This is all I need. Degree d would be d times h. I'm being rather sloppy here. Let me maybe for once try to put a notation. Say that I is the embedding of, then what I'm doing is really after we push forward to the ambient. So you see, this is the computation you would do if you wanted to compute the Chern class of Tx reg, I don't know how to call it, in period, where this is a smooth hypersurface of degree d. So in particular, its degree, which is what you asked about, would be the Euler characteristic of a smoothing. To some extent, this you can make a more general statement, of course, but I think this captures something that is going on. If you have a local computing intersection, you have a virtual tangent bundle. This is the class of the virtual tangent bundle. Maybe that's a quick way of saying it. Okay, so for example, if you take a degree 3 curve, what's CF of the nodal cubic that gave us the calculatrice a moment ago, this is the same as after we push it forward to projective space as the class of an elliptic curve. Tangent bundle elliptic curve, we just write the 3 class, the class of P1 plus Euler characteristic, which is 0 for elliptic curve times 0. So these things are computable. To some extent, if you have some information, this does not involve difficult computations. Okay, thanks for asking. So I had a little more time to spend on that, but I want to talk about something else. Questions? This is, again, the end of the topic. I'm in big trouble. Let's see if I can at least go through this. We are soon going back to high school algebra because I like that. So I introduced classes with this example from enumerative geometry, and there we wanted to evaluate the contribution of a connected component to an intersection. Well, maybe you are not so lucky. Maybe your component is not connected. Maybe you're in a situation in which you have something that is disturbing your situation, and you would like to understand the contribution of this to a Segre class or to an enumerative problem. So the question I'm posing is, suppose that a scheme, do I have notation for this? Probably I should follow my notation. Suppose you have y1 and y2. Suppose y is y1, union y2, not necessarily disjoint. And then a general question is, can you compute, and everything happens as usual in my M invariant V. SYV is that in some way related to, the question would be relate this to S of y1 V and S of y2 V. Now, people in this room have looked at this. Stephen, for example, I think has worked on this. It clearly depends on how they intersect, right? If they are disjoint, then this is the sum of these two guys, essentially. If they're not disjoint, something happens, and we want to understand if we can control that. So this was my y1, this is my y2, maybe, I don't know. And we would like to understand in what sense we can have these two guys play off each other to get this. And I'm not going to give a general formula because I don't know we need a general formula for this. But if you keep in mind the birational invariance of Segre class, you are allowed to blow things up, and that means that at least you can probably reduce yourself to the case in which one of these two guys is a divisor. So let me assume that, and let me change my notation. Assume you have W equals D union Y, and D is a divisor. What do I mean by this? I mean a scheme-theoretic statement. I mean that the ideal, locally, maybe the ideal of D is principal. And all I'm writing is that, I don't know, how should I write it? The ideal of Y will have some generators. And then this identity here means that the ideal of W is the product of those generators by the generator of D. I could say that I suppose Y is the residual scheme of D in W. Maybe that's the terminology. This is the picture I have in mind. This now is D. It's a big fat thing. This is my Y, and this whole thing is W. Okay? So the question is, what can you say about the Segre class of W in V? That's the question. For the answer, I can give you the answer. Here's the answer. Let me give you the dimension M piece of the Segre class. And here it is. It's, after all, the divisor is big, so take most of it. But there is a correction that comes from the other piece, and here it is, summation j equals 0 to k minus m, binomial k minus m, choose j, minus d to the j, and then s, y, v, component of dimension m plus j. M is the piece of dimension m. It's an index. K is... what's K? No, what's K? That's a very good question. What's K? Why is it not in my notes? It's, maybe Steve can help, or maybe you can help, because it's in chapter 9 of Fulton's book. Why is K, what's K? Let's see.
Here.
Do you have chapter 9?
Yes. Here. Where in chapter 9?
I think 9.1.2 will do or something.
You kill me.
9.1.
Bottom left. Are you saying it's here? No.
Actually, the point I'm trying to make is that you don't need to know this formula. And indeed, you see, I do not know it myself, and I'm a little surprised that this is happening right now. Can you find the formula?
I'll look. He's looking.
Here it is. V is, K is the dimension of V, yes, or of Y, I suppose, in this case, right?
No.
In any case, the message I'm trying to convey is that you don't need to remember this.
No, it's the dimension of V.
But probably my V is
Position 9.2.
9.2. Oh, okay.
Yeah, keep down, it's the dimension of V.
You're right, dimension V. You can tell how, yeah, even with notation. So this is a beautiful formula. I will tell you in a moment why it is true, and you could prove it yourself. So if I'm wrong here, you will find that I'm wrong. But the next message I would like to convey is that you don't need to worry about it. It looks like I will begin telling you why today, right now, and continue in about half hour. Because there's notation, easier notation to remember that will take care of this kind of formulas. What makes this a little difficult to remember or apply are the binomial coefficients, of course. It's a little hard to remember the right binomial coefficients, and if you start applying this in actual situations, you will find yourself filling your pages with binomial coefficients and summation of binomial coefficients. That's not necessarily good. So I'm going to try to convince you that that's not can be bypassed. What's the proof? Well, I told you you would reduce this to this situation by blowing up, but nothing prevents you from blowing up again. So blow up along y, the other thing. Then you'll find yourself in this situation by inverse of the divisor, union, exceptional divisor, dominates w in V, and here's a blow up. Right? Now if you E is the inverse image of y, this is the inverse image of d, w is concocted as the union of those two things. That remains true upstairs. Or if you want, look at this. No, upstairs, this E1 through ER becomes principal, becomes the equation of the exceptional divisor, and this is just the scheme given by f times that equation. Okay, so that would tell you that S of W P is the push forward of, by now we know the drill. This is a birational map. And this is a divisor, so all I need to do is to compute the push forward of the upper star of D plus E over 1 plus pi upper star D plus E. And if you do this, you get the formula. This is easy to believe, right? As you divide by something and work it out, binomial coefficients are coming out, and do it yourself. That's what you get. This plus sign is the reason why there's a minus sign over here, once to invert the power series. Right? It's perfectly believable that that comes out of this. So this is perfect. There's nothing, absolutely nothing unpleasant about it, except that I cannot remember this formula, as you saw, right? And that it is a little hard to manipulate. So before taking a break, because I still have a couple of minutes, let me just put on the board notation that I promise will allow us to dispose of this. In fact, I will not come back to this, so I can erase it. Okay, I'm not writing this, but what I'm doing over here, one of the purposes is to make this kind of computation easier. These are notations for which I don't have any other reference than my papers. I use it all the time. I'm also basically the only person on the planet to use them, almost, I think. So here I'm given a class, call it A, and I write it in terms of its components. For some reason, this is happening all in a variety. V, and it's good to keep track of V. So this is the component of codimension I in V, although this class is a class in the Char group of something, say Z is inside. Keep in mind that there is this ambient variety V fixed, and this alpha I is the piece of codimension I in the ambient variety V. This was the choice I made when I introduced these. May not be the best choice, but so the notation is very simple. if I write a check, what I mean is the same class, but you change the signs of the terms in codimension I. Unfortunately, I don't know where to put v here. This is not a v, this is a check as in dual. I'm just changing the sign of every other term. And I'm also given a line bundle on Z. And if I write a tensor L, if I remember, usually I don't remember, I will put a reminder to me that I'm doing this in an ambient variety V, because I need to know what I means. That's the summation of alpha I divided by the ith power of the total chunk class of L. So I'm not doing anything like dividing by a class. This is a formal operation. This is 1 over 1 plus the first chunk class. You expand that, take the ith power, and so on. So there's a little calculus associated with these notations, properties. These are easy exercises. Let's see, I have a couple here. Maybe I can fit them all in here. Number one, this operation of tensoring is in fact an action. By which I mean that if you start with A, tensor with L, and then tensor with M, that's as good as tensoring A by L tensor M. This is why I call this thing tensor, because it's compatible with tensors in this respect. What is this? This is just a silly binomial coefficient game, because you just have to write this and explain it out and check that it is true. Second remark, is this okay for the audience, or should I write it? I want to remember that this is what I want to do. Let me. I'm not using the board as efficiently as I should. Second property would be, now suppose that you have vector bundles around. E and F are vector bundles on Z, then I claim that this tensor is compatible with tensoring the vector bundles by the line bundle. And that there's a little twist in the story. Suppose you have this situation. What happens if you tensor by L? Well, if you're very optimistic, you might think that all you need to do is bring the tensor in. So this should be C of E tensor L over C of F tensor L cap A tensor L. That's not true. That's why I left a little bit of room in here. It is true if E and F have the same rank. Otherwise, you have to account for the difference in ranks, and that would be C of L. I need to pretend that these are rank 0, so I need to provide the rank of help F minus the rank of E. Is this still readable? Not so readable. Let's try again. So you can bring L in, but you have to be careful about the ranks. And there's a third observation, which is very easy. I'm erasing the notation. I'll probably put it again on the board in a moment. Things such as if this is proper birational, then doing the tensor before or after gives you the same result. And you could write more of these. This is so simple that nothing really is going on. Now I see that my time for the first hour is certainly up, so I'll give this. I'll leave this cliffhanger, how to use those things to attack this guy. Okay, so we'll see that in about a half hour. Thank you for your attention.